Welcome to the next lecture in electric circuit analysis. In this lecture, we will focus our discussion on magnetically coupled circuits. Let us see the introduction first. So, we have been discussing the conductively coupled circuit till now. So, what is the meaning of conductively coupled? If one loop where the current is flowing affects the neighboring loop through current conduction only, then in that case we say that the circuit is conductively coupled. So the current conduction phenomena is there through which one loop is affecting the other loop. On the other hand, if there are two loops which may or may not be in contact to each other, then in that case, if one of them is affecting the other through the magnetic field linkage between the two loops, then that is said to be magnetically coupled circuit. So here the main point is the circuit may be connected or the loop may be connected or may not be connected. However, the magnetic field between the two loops should be connected. In that case, the conduction effect will be there, and that is due to the magnetically coupled network. We know that for the AC or the DC current which is flowing through a conductor, there will be some magnetic field which will be generated about the conductor. Now, in the circuit context, we say that the magnetic flux, which is represented by phi, is equal to the average normal component of the flux density given by Bn multiplied with the surface area of the loop given by A. So sometimes we use the term magnetic field, sometimes we use the term magnetic flux. So both in the circuit context will be same, and we will use the equation of flux is equal to the magnetic flux density multiplied with the area of the loop. So phi is equal to B into A. This is the famous equation of flux. Now, if a time varying flux means the flux is a function of time t. So when the flux is varying with respect to time t and it is generated by one loop, it is penetrating a second loop. Then in that case, there will be a voltage which will be induced between the ends of the second wire. So let us see with this a diagram. Now this is my one coil where I am supplying some voltage V, and as a result a current is flowing through it. Now this coil will have some inductance which is given by L. Now let us suppose there is another coil which is in the close vicinity. It will also have some inductance. Now I will represent this one as L1, this one as L2. So the supply voltage I can take this one as V1 and the current I will take I1. Now if the two coils are related to each other with the magnetic flux which is common between the two coils, then in that case, due to the Faraday's law of electromagnetic induction, there will be some voltage produced in the second coil. Now if we are connecting a load in the second coil to complete the circuit, then in that case there will be a current flowing in the second coil. If the load is 0, it means there is no load, so the current will also be 0. So under the condition of no load condition, we will be having the current to be flowing to be 0, but there will be some definite voltage which is due to the magnetic induction, and hence we can say that the magnetically coupled circuit where these two circuits are not linked to each other conductively, rather than they are conductively linked together. Now we have already discussed the concept of self-inductance, which is otherwise known as normal inductance only, and we now want to distinguish one more term that is known as mutual inductance. Here one thing has to be noted that there is no such device as a mutual inductor. So we don't say that there is a device known having a mutual inductor. This is a phenomena which is occurring when the two coils are in close vicinity and there is a magnetic flux which is linking the two coils. So there is no such device as a mutual inductor. Now always we know that transformer has the basis concept of magnetic coupling. So the principle over which a transformer operates there has to be some magnetic coupling between the primary and the secondary coil of the transformer. So transformer is the most efficient example when we are discussing the concept of mutual inductance. Now let us differentiate the self and the mutual inductance. So how do we define mutual inductance? If two coils, which are known as two inductors, are in a close proximity to each other, then the magnetic flux which is caused by the current in one coil. So when the current is flowing in one coil, it will lead to a magnetic flux phi which will link to the other coil, and thereby it will induce a voltage in the second coil. This linking of the first coil to the second coil will be due to the common magnetic flux, and these phenomena is known as mutual inductance, and the inductor is known as mutual inductance. So let us have a quick revision what we have discussed when we took the topic of self-inductance. So if a coil is there which is having an inductance of L, now if a source of a current is flowing, due to which there will be the flux generated in the coil. So we know that the voltage is equal to N d phi by dt from the principle of Faraday's law of electromagnetic induction. So here we have the self-induction, and due to which the voltage is induced. Now we try to divide with di terms on the both sides, on the numerator and the denominator. So we get that the voltage is equal to L di by dt across the inductor. So across the inductor the voltage will be L di by dt, and the inductance will be N d phi by di. So the rate of change of the flux d phi with respect to the current di multiplied with the number of turns in the coil will give you the self-inductance. Now here we have only one coil, so we are saying that the self-inductance of the coil. On the other hand, if there are two coils which are in close proximity or vicinity having number of turns N1 and N2, and in the first coil we are supplying some current, since both the flux are linking with the same magnetic flux, hence the voltage will be induced in the second coil given by V2. So the primary flux V phi 1 will be the summation of two flux. One flux is due to the current flowing in the coil L1, and one flux which is common between the two coils given by phi 1 2. Now the voltage induced in each coil V1 and V2 will be similar to what we have discussed for the self-inductance of a single coil. Then we can have the voltage induced in the first coil will be L1 d I1 by dt, whereas the voltage induced in the second coil is as a result of the mutual flux which is linking the first coil and the second coil, and hence here we will be having a term known as M to 1, which is the mutual inductance. Otherwise, concept basis the voltage will remain the same. Only difference is that in the first coil we have the self-inductance, whereas in the second coil we have the mutual inductance due to which the voltage is induced. So we can write M to 1, that is mutual inductance in the second coil due to the current flowing in the first coil, is equal to N2 d phi 1 2, that is the flux linking 1 2 by di1. So here the current is flowing in the first coil and flux is linking both the coil, and voltage is induced in the second coil V2. So if we observe the two equations of self-inductance and the mutual inductance, both are looking the same, with only one difference is that in the self-inductance the flux is linking the coil 1 only, whereas in the mutual inductance the flux will be linking the both the coils. Then we will have the mutual inductance principle. Now here in this example we have taken that the current is given to the primary coil or the first coil, whereas there is no current in the second coil because there is no load connected to it and it is open circuit. Whereas if we do the other part, that is giving the current to the second coil and keeping the first coil open, then we will be having the same formula Only difference is that the current is flowing in the second coil now, and the flux is same, that is the flux linking due to phi12 will be equal to phi21, and also the mutual inductance M12 equal to M21 is equal to M, because the same flux is linking both the coils. So the mutual inductance is measured in Henry, similar to the self-inductance. Mutual coupling only exists when the inductors or the coils are in close proximity. If the coils are very far away, like for example, we have the first coil which is having a self-inductance L1 and the second coil L2 which is very far. So the flux may not link. So we have the flux phi1 here and the second flux phi2 here, and there is no mutual flux linking the first coil and the second coil. And as a result, mutual inductance will not take place. Hence, the close proximity of the coil is an essential parameter. Also, the circuit has to be driven by time varying source. Like here, we have given the current which is a function of time. If time varying sources are not connected, then mutual flux will not be developed, because we required a flux which is also time varying in nature. Then only the Faraday's law will operate. Now, we can understand that the mutual inductance M is always a positive quantity, just like the self-inductance L. However, the voltage which is induced due to the mutual inductance M di by dt may be positive or negative in accordance with passive sign convention. So, polarity of L di by dt, that is the voltage induced due to the self-inductance, we can determine using the passive sign convention. But the polarity of mutual voltage, that is M di by dt, cannot be determined by the passive sign convention, because the four terminals are involved now. How four terminals are involved? Suppose we have the first coil here and the second coil is here. So if I take these 1, 2 as the first terminal, then we will have 3, 4 as the second terminal. So in total we are having the four terminals involved, and hence passive sign convention will not be useful in order to determine the polarity of the voltage induced due to the mutual inductance. Then how do we determine this polarity? So the polarity determination can be done by examining the physical orientation of both coils, how the coils are oriented, and also we apply the Lenz's law in conjunction with right hand thumb rule. So we have different laws of magnetics which we apply for the four terminal device in order to find the polarity of the voltage induced due to the mutual induction. Now we use one concept known as dot convention to determine the mutual inductance polarity as well as the current. Now four different orientation of the coils may be there in accordance with how the current is flowing in the coils. If the dot, now let us take the first case. In the first case we can see that the current I1 is entering a dot in the first coil L1, and the voltage V2 positive polarity is in the same way as the dot where the coil is placed. We will just understand this dot in more detail a little bit later, but let us observe the circuit first. In the second case, what is happening, the dot are opposite to each other, so it is diagonal, so the current is entering the first dot, whereas the positive voltage is in the non-dot position. Third case, C case, we can see that the current here is not entering the dotted terminal, however the positive polarity of the voltage is in the dotted position. Fourth case, if you see that current is not entering the dotted position and the positive polarity is also not in the dotted positions. Four possibilities are there by which the polarity of the voltage as well as the current flow can be there. So here accordingly we can see that the voltage induced may be positive or negative in all the four cases. Now let us understand how and what it is happening. So the famous dot convention says that if a current is entering the dotted terminal, like here we have a dotted terminal where the current is entering. to one coil, it will produce an open circuit voltage, because here we have the open circuit condition in the second coil with a positive voltage reference at the dotted terminal of the second coil. So wherever we have the positive polarity, it will be occurring at the dotted terminal. Now, if the current is entering the undotted terminal, so if you see the case C, current is entering the undotted terminal, then of one coil, then a voltage that is positively sensed at the undotted terminal. So at the undotted terminal, you will be having the positive, and here you will be having the negative side. Okay, so that is what the two cases have been given, and all the four orientation will come from there. So we have to see that where the current is entering first in the first coil, whether it is entering the dotted terminal or whether it is entering the undotted terminal. Then we can decide the polarity of the voltage of positive and negative sign, how it would be with respect to the dot. So this is known as dot convention, and these two rules will be obeyed to find the polarity of the voltage with respect to the mutual inductance. Now there is something called series adding circuit and series opposing circuit. What are they? Let us take the two cases, case A and case B, where in the case A, if you see, the current is entering the positive dotted terminal at the first coil, and in the second coil also the current is entering the dotted terminal. So this is case A. It means it is a series adding connection where both the inductance are adding in terms of mutual. Then we have the total inductance. If we try to calculate at the terminal, that is the net equivalent inductance, will get L1 plus L2 plus 2M, because we have the mutual inductance between the coil 1 and 2. So 2 times it would be from the primary coil to the secondary coil, or L1 L2, and then here this side you will be having L2 L1. So that is the reason we say 2M and a positive sign. Now series opposing network, like for example, if the current is entering the dotted terminal of the coil L1, but it is not happening the same thing at the coil L2. The current is entering the undotted terminal here. Hence, we will be having a negative sign when we try to determine the net inductance at the terminals. So this is known as series opposing connection, where we have L1 plus L2 in the two coils, self-inductance and minus of 2M. So in general, we can say that it will be L1 plus L2 plus minus 2M, plus for series adding connection and negative for series opposing connection. So we discussed the self-inductance and mutual inductance separately. However, let us combine both to determine that. Now let us see the first case. Here we have the two coils having inductance L1 and L2, that is the self-inductance, and M is the mutual inductance. So what is the voltage V1? So we will be writing the KVL equation in the first loop and try to determine the voltage V1. So V1 will be equal to L1 di1 by dt. This is due to the self-inductance, and M times di2 by dt, because in the first coil the mutual inductance will be due to the current flowing in the second coil. Whereas if we try to determine V2 here, then we will have the self-inductance due to the coil 2 and mutual inductance due to the current flowing in the first coil. Also, we can see that both the current are entering the dotted terminal, so we are having the positive sign of the polarity of the voltage. So we have positive polarity of the voltage. Now on the other hand, if we see that if the current is entering the dotted terminal one coil and other coil the current is leaving the dotted terminal, then in that case the polarity will be little bit different. So here we can apply the KVL for the two loop V1 and V2 we can determine. So self-inductance of the coil 1, we will be having a negative polarity, and mutual inductance will be M di by dt. Now here the current is due to the second coil. Current flowing in the second coil will give the voltage V1. And in the V2 we will be having the first current, and there will be a negative sign here. So two possibilities of connections are there. So we can apply the KVL equation and determine the voltage due to self-inductance and voltage due to mutual inductance to combine together to form the net voltage in the first and the second. Now here we have not taken any drop into account. Now we can take that there is a resistive drop due to the coil resistance. In that case, we have to add I1 R1, that is the voltage drop in the resistance of the first coil. And if you have the coil resistance R2 here, then there is a drop of I2 R2. So depending upon what type of elements are involved in the circuit connection, we can write down the equations of the voltage. Now this is in the time domain. So we have written the equation in time domain. What about the frequency domain? So in the frequency domain, our time domain counterpart will be converting to the frequency domain, where we will be having d by dt term converted to j omega term. Okay, so we will be having d by dt term converted to j omega term, and hence we can write it in this manner, where we convert the time domain counterpart into the S domain or the frequency domain. It is always easy to solve in the frequency domain as compared to the time domain. Now let us see the energy in a coupled circuit. We already have learned the energy present in the inductance, that is equal to half of Li square. Now here we have only the self-inductance term. What about the two coils when mutual inductance is present between them? Now we assume the condition that the current, initially that there is no current present in the two coils, and hence the energy will be zero under the initial conditions. Two coils are there, L1 and L2, where the currents are flowing to the dotted terminal, and we have the mutual inductance which is present between the two coils. Now considering that we increase the current I1, now here the current I1 is flowing in the first coil, increasing the current from 0 to capital I1 and maintaining the second current to be 0. So in this first case, we will be having no current flowing in the second coil. Then we know that power in the first coil will be the product of voltage and the current, and we can write the voltage in the first coil is equal to L1 di1 by dt, because we have only the self-inductance now. So the energy is basically the integral of the power, and we integrate the power with respect to the current, that is I1 d1, from 0 to capital I1, because we are varying from 0 to I1 the current. Hence the energy present is half Li square, and subscript 1 has been used for the first coil. Now if we maintain the first coil to a current I1, whereas the current I2 now is increased from 0 to I2, then we now find the power in the second coil. First we have found the power in the first coil. Now we are trying to find the power in the second coil, which is equal to, we already have some power in presently due to the self-inductance. Now we will be having due to the mutual inductance, and we can obtain that two terms and integrate the term as it is from 0 to I2. Then we have the term half L2 I2 square. This is due to the self-inductance, and mutual inductance I1 to I2. Due to the mutual inductance, we will have some energy. Now the total stored energy we can calculate as the sum of energy that we have got from the first coil and the second coil, and we will be having the first two terms is due to the self-inductance of the first coil and the second coil, and the last term is due to the mutual inductance which is linking the two coils. So if the mutual inductance is not there, then this effect will not be there, and the energy will be due to the self-inductance only. And if the mutual inductance is there between the two coils, then we will be having the third term. So here we derive the equation assuming that both coil currents entering the dotted terminal. So we have seen that both dotted terminal we enter the current, and then we have derived the equation. We could have derived in some other manner also, like if one current is entering the dotted terminal while the other current is leaving the dotted terminal, then the mutual voltage will be negative. So here we have the positive sign, which would have become the negative sign when the current is flowing in the other way around. So for the net equation, if we want to write, like we have varied the current from 0 to I1. So I1 and I2 are both arbitrary values. So it can be replaced with the net current I1 and I2, which are instantaneous energy stored we want to calculate, and the general formula will have the cell energy due to the first coil and self energy due to the second coil, and the mutual energy with positive negative sign in order by which the current is flowing in the first coil and the second coil. Now question is, what is the upper limit for the mutual inductance? We have to understand what should be the upper limit by which the mutual inductance will be present in the two coils. So we know that the circuit is passive in nature. So energy cannot be negative. So the net sum of the energy has to be always positive and greater than equal to 0. So if we complete this equation to be a perfect square, then we will be having the equation like this, and it has to be equal to greater than 0. If you observe the first term, since the square term is there, it is always greater than 0. This is a positive quantity, and here we have to see these quantity to determine whether it is positive or negative. Now we have to make the overall equation to be positive. It means the second term we have to make to be positive, that is under root L1 L2 minus m has to be greater than 0. If we rearrange this term, we can write m, that is the mutual inductance, should be less than under root of L1 L2. Now what is the meaning of this? We will see a little bit later. Now there should be some constant term which is known as coefficient of coupling, where the mutual effect will be m by under root of L1 L2. So the mutual inductance is equal to k times under root L1 L2, where k can be varied from 0 to 1 and m can be varied from 0 to under root of L1 L2. The meaning is mutual inductance cannot be greater than the geometric mean of the self-inductance of the coil. So geometric mean we are calculating as the product of the two inductance and taking the square root. So this is the geometric mean of the two inductance. Hence, the mutual inductance cannot be greater than the geometric mean of the two self-inductance. Also, the extent to which the m approaches the upper limit is specified by the coefficient of coupling. So this k value, that is the coefficient of coupling given by this equation, will determine how the m is approaching to the upper limit. Now, if we try to define what is coupling coefficient in terms of flux, let us see that. So we have taken two different windings and the coils present in the core, and the core is of air or ferrite core, any type of core we can use. In the first case, the coils are loosely coupled, whereas in the second coil, the coils are tightly coupled. Now, what are the meaning of loosely coupled and tightly coupled? We will see it. Coupling coefficient is defined as the fraction of the total flux which is emanating from one coil that links to the other coil. So we have two coils here, and there will be some mutual flux linking the first coil and the second coil. So the coefficient of coupling can be defined as, it is the ratio of how the flux is linking the two coils. So phi 12 is the flux which is linking the coil 12 divided by the flux 1, that is the total flux in the first coil. And the total flux in the first coil can be written as phi 11 plus phi 1. Other way around, if we are going from the second coil concept, then on the numerator we will be having phi 21, and on the denominator we have phi 2, whereas phi 2 is equal to phi 21 plus phi 22, and on the numerator we have phi 21. So we can say that if the entire flux which is produced by one coil, so this is the first coil where the flux is produced, if it is entirely linking the second coil, then the coefficient of coupling k is equal to 1, and we say that it is 100% coupled or the perfectly coupled coil. So this is the ideal condition where we have the perfectly coupled coils. On the other hand, if the value of k is less than 0.5, then we say the coils are loosely coupled, whereas k greater than 0.5, the coil is tightly coupled. So three different conditions can be there. So here we can see there is a much gap between the first coil and the second coil, or the distance between the first and the second coil is more, so it is loosely coupled, whereas the first and the second coil are tightly coupled in the second case. Now we say that transformer is one of the most important apparatus which use the concept of mutual coupling. So let us see the linear transformer coupled circuit, how it will be and what is their functioning. So in a transformer, we will be having two coils. One is known as the primary coil and another is the secondary coil, having the inductance L1 and L2. And in the primary coil, we are giving the source of the EMF, which is deriving the current I1 in the primary coil, and in the secondary coil we are connecting the load. So due to the mutual inductance, there will be some voltage produced in the secondary coil, and if the load is connected to complete the circuit, then the secondary current will flow in the load. So if we write the KVL equations in the first and the second loop in the frequency domain, we will be getting the equations like this, where the voltage is given in the primary coil, and in the secondary coil we are not having any source. Now, if we want to determine the input impedance of this transformer, we can determine by using the input voltage by input current. We will be getting this equation. So if we observe this equation for a normal circuit which is not having any mutual inductance, if M is 0, we should get R1 plus J omega L1, because we have R1 here and J omega L1, which is giving me the input impedance in the first coil. But due to the presence of mutual inductance, the second coil will have some effect on the first coil, which is given by this equation. So what is this equation? Thus, this term which is impacting the input impedance of the first coil is known as the reflected impedance. So if mutual inductance is 0, there is no mutual coupling in the first coil and the second coil, then we will be having the ZR, that is reflected impedance, to be 0, and the entire input impedance will be equal to the normal circuit constant R1 plus JXL1. And due to the mutual inductance, the reflected impedance will impact the first winding. Now let us observe the reflected impedance term. Here we have the term M square. So it means that location of dot does not affect. If we place M or minus M, it doesn't mean, because it will be a positive quantity. However, when we try to analyze any magnetically coupled circuit, we see that it is not very easy or straightforward in nature. Hence, what we do is that at some times we convenient to replace it with equivalent circuit without no magnetic coupling. So I don't want this mutual inductance which is present in the first coil and the second coil, and I want some equivalent circuit of the coupled circuit without mutual coupling. So I want to eliminate the mutual inductance. So in order to eliminate the mutual inductance, what we do is that first we will take the mutually coupled inductors and try to write the equation V equal to Zi. Also, we try to write the same equation in terms of current, that is I is equal to Y into V, where Z is the impedance and Y is the admittance. So I will be getting the equation like this. In the first equation, we have the V equal to Zi, where Z impedance matrix we are getting. If we take the inverse of this, we'll get the current is equal to admittance into voltage. Now we will use these equations to try to get some equivalent circuit where the mutual coupling is not there. So two different circuits we are going to see. The first circuit is a T circuit where we want to determine the values of these inductor LA, LB and LC, so that the circuit looks like a T circuit, and we want to determine these values of LA, LB and LC in terms of L1, L2 and M, so that we get one circuit without mutual coupling. So if for this circuit, if we try to write the equation of V equal to Zi here, that is the Ohm's law, and we try to equate these with the normal equation that we got for the mutually coupled circuit, then we can equate that the LA value is equal to L1 minus M, this inductor LA, LB equal to L2 minus M and LC equal to M. So given the value of L1, L2 and M, we can obtain an equivalent circuit in the form of a T circuit nature, where the inductances will be in the form of L1 minus M, L2 minus M and M, which is the mutual value between the two circuits. So this circuit will not have any mutual coupling, and we can do the analysis in a better way compared to the first circuit. There is one other way we can do it, that is the pi circuit. So in the pi circuit, we have the circuit in the form of a pi, where LA, LB and LC can be determined from the current equation. So from this circuit, we can write the equation of the current is equal to admittance into voltage, and these admittance matrix we can compare with the previous admittance matrix that we have got for the coupled circuit to determine the value of LA, LB and LC. So we can get the value of LA, LB and LC, and we can create a pi circuit where there is no mutual coupling, and we can analyze that circuit in a much better way. So this completes our discussion on mutual circuit. So combining the self-inductance and mutual inductance, we can determine the voltage, current and the impedance of any mutually coupled network. Thank you for now.